So at the end of the last lesson, I mentioned briefly about when we talk about parallel streams. Needless to say, we'll do probably a couple weeks of this course on parallel streams because that's really important. But right now I'm going to give you a head start on this because assignment 1B will use parallel streams, and it's important to be aware of what they are. So there's two basic types of streams. There are sequential streams, which is what you get by default, and then there's parallel streams, which you get if you say parallel stream or dot parallel. And we're going to talk in this lesson about what parallel streams are briefly, and then we'll also talk about some of the common programming hazards that can arise when you start using parallel streams and you don't keep in mind certain things like you really need to make your operations stateless. Very important. Or your behavior stateless. So by default, stream operations run sequentially, and that's what we're going to focus on, today and probably maybe next time before we shift gears. And to get a stream that's a sequential stream, you just say dot stream. There's other ways to do it, but that's probably the most common way to do it. So if you have a collection, for example, you can say dot stream. It makes it a sequential stream, which means there's one thread, and that thread will run on a core. It could be time sliced on different cores, but only one core will be used at any given time to process that stream. You can also have parallel streams. The easiest way to get a parallel stream is to say dot parallel stream instead of dot stream. There are other ways to do it too, but that's the easiest way. And in that case, what's going to happen is we're actually going to end up with a pool of threads being used. And this pool of threads comes from something called the common fork join pool. And that pool of threads will be used to process the elements in the stream. And it'll do it using something called splitterators, which we'll talk about later, which take the original data source and split it up into chunks. And then it gives those chunks to threads in the fork join pool, and those threads then process the operations in parallel. And then there's ultimately some kind of joining or combining phase at the end to put them all back together again to a final result. So a parallel stream internally uses something called a splitterator to split the elements, the data source, into multiple chunks. And then it also uses something called the common fork join pool to process these chunks independently. This goes back to a good question we talked about a few minutes ago about the difference between split, apply, combine, and fork join. So the splitting phase in this model will create chunks which are fed to the fork join pool, and then the fork join pool will process or apply the various elements, the operations in the stream in parallel. And then when everything's done, it'll join it together for the combined phase. So that everything works together nicely under the hood. Yes, ma'am? Oh, great question. So the question is, when we talk about split, apply, combine, are we talking about sequential streams? Are we talking about parallel streams? So when I say split, apply, combine, it applies to everything. We're starting with sequential streams, so I used that to begin with. But splitting and combining is most important for parallel streams. For sequential streams, it's kind of a no-brainer because there's really nothing much to do because you're all processing in one thread. When we get to parallel streams, splitting and combining do really interesting things. They also do things too for sequential streams, but it's not as interesting. So the question is, does the fork join pool apply to parallel streams? You can think about a sequential stream as being a fork join pool with a single thread, with just one thread in it. Yeah, exactly. That's a good way to look at it. And this is a nice little picture of the common fork join pool. And as I mentioned before, the way it works under the hood is you've got a pool of worker threads. That's why we have the pool icon. And these are the little thread icons. And each thread has a double-ended queue called a deck. And in that deck is work for each thread to work on, which I call subtasks. And if one thread gets to a point where it's got nothing else in its deck, then it will go ahead and steal or try to steal a task at the end of somebody else's deck. So when it's, and the idea there is to try to keep the process utilization as high as possible because you want to make those cores, earn their living. You want to make them work for their, sing for their supper, if you will. Now, this goes back to another earlier question we discussed. What's the pros and cons of the different approaches? And this is an example we'll take a look at in more detail later. This is called Search Stream Gang Program. And it basically reads in complete works of Shakespeare all 38 plays and sonnets. And then you can do queries to find where famous phrases in Shakespeare match in which works. And this is a test I conducted some time ago on an earlier laptop I had that was a quad-core laptop with 32 gigabytes of RAM. My current laptop is an 8-core with 128 gigabytes of RAM, so it's pretty hefty. And the main thing you'll see is what I'm about to talk about. So these are all the different models of concurrency that we use here. And this is the sequential version, streams. And this is the sequential version with loops. And to the question that was asked earlier, you can see that using the loops is a little faster than using the streams when you just look at it, one thread sequentially. It's not like wildly faster, but it's faster. But, and here's the big benefit, when we turn on parallel stream, then all of a sudden, look at the huge boost in performance. So in this context, lower numbers better. We did more work in less time. And so, even though we get a slightly better performance of sequential loops versus sequential streams, when we turn on parallel stuff, which is to do, we get a huge, basically, n-fold increase. We basically are speeding up essentially linearly. Better than linearly because this is actually a hyper-threaded computer system. So each core has 2 hyper-threaded cores. Yes, sir? So the question is it possible to quantify the benefits of using parallel streams? Absolutely, yes. I mean, this is one example of that. So I have the little test framework that measures the time taken to do the processing, and we start a timer, we run the test, we stop the timer, we see the results for each of these things. So yes, you can. Although, was your question more like, okay, so you want to look at it more from an algorithmic complexity point of view. Yes, again, so if the question is, can you quantify it? Absolutely. So this particular type of processing is something that's called embarrassingly parallel. If you recall, embarrassingly parallel processing just means that there's no dependency between the tasks. Each thing runs independently. So, an easy way to do it is, if you know how long it takes to run some processing step for one thread, then if it's an embarrassingly parallel processing task, and you have n threads, n cores, then it should take, roughly, whatever the time is divided by the number of cores. Now, it's sometimes not 100% linear because there are situations where there's other overheads of parallelism having to do with splitting, for example, and combining and so on. And as they say with fuel efficiency estimates on car stickers, your mileage may vary, right? It's 25 miles per gallon on the highway and you get 28 or 23. Your mileage may vary based on factors like how fast you drive or how good your gasoline is or whether you keep your oil changed or whatnot. So there's slight differences, but yes, you can certainly quantify those things. My personal recommendation is to benchmark them using things like the Java Micro Benchmarking Harness, JMH, and then see how they run faster or slower. And there's really cool ways we'll see later to automatically turn parallelism on or off in a very fine-grained way, so you can see what it performs with sequential. You can change a Boolean flag when you run the test program. You can see how it performs with parallel, and then you decide which one you'd rather use. And for most non-trivial applications, parallelism on a modern multi-core processor will give you a big boost in performance. Not always, but often. Okay, next topic here is, what are some common programming hazards for parallel streams? So as we've talked about, ideally we want the behavior's output in a stream to only depend on its input. And that's another way of saying that, which is a better way of saying it perhaps, is we don't want side effects. So side effects are what occurs if you stash state or you keep shared state or you put things off to the side so that as stuff happens, there's history, there's side effects, there's other stuff besides just the function processing the input and the output determining what the results will be. So here's our good friend capitalize. Now we can see what it looks like. So you can see that capitalize is a great example of a side effect-free method where it's going to take a string S. If the string has a length of 0, we just return it, because what's the point of capitalizing a string that's got nothing in it? Otherwise, we convert the first character in the string to uppercase, and then we take the rest of the string and we lowercase it. And then we append the rest of the string to the first character that was uppercased. So this is actually showing off a whole bunch of interesting things. It's also demonstrating the fact that in Java, Java strings are immutable objects. So once you create a Java string, you can never modify it. You can only create a substring and then concatenate things back together again to make a new string. This also demonstrates that there are no side effects. We're not storing anything in a local variable, like a local static variable. We're not sticking something into a map or a set or some field. It just get the input, process it, and return the result. So that's what's called a side effect-free method. And those are what you want. Why do you want those things? Because when we move to parallel streams, if you have behaviors with side effects, they can lead to race conditions. And we've talked about race conditions before as one of the examples of hazards in concurrent programs. But basically, a race condition can arise in software when an application, or not a piece of code, doesn't have to be an app, but it could be a system software, whatever it is, depends on the sequence or the timing of threads for it to operate properly. So if you only get the right result when the moon is in a certain phase, or you throw salt over your shoulder, or you don't walk under a ladder, or you avoid the black cat on Friday the 13th, whatever the superstition you have, if that's the only time your program is going to work right, then you probably have race conditions. And race conditions most commonly occur when you have shared mutable state, which is the root of all evil in concurrent and parallel programs. And what happens in that case is that multiple threads will come and read and write from a common field or a common global variable or whatever language you're in. And because they're not protected by synchronization, the state will be corrupted. And I'll show you an example of this in a second to make it more clear. So here's an example of computing n factorial using a buggy approach that has shared mutable state. And you can find this example here in my GitHub, EX60. So it's going to try to compute the n factorial. Now this will work fine if we have sequential streams, but if we have parallel streams, as we do here, it'll cause problems. So here's the shared mutable state we're talking about. We've got ourselves a class called total, and the class called total has a public field called mtotal, which we assign to 1, and it's got a mult method that takes a long n and multiplies mtotal by n and assigns to mtotal. And you will notice there's no synchronized keyword here, there's no reentrant lock, there's no atomic this, that, or the other thing. It's just doing an update to a field. It's unprotected. Down here we make ourselves an instance of total. This is the shared mutable state. And then we're going to go ahead and have a stream. And by the way, if you want to find out why shared mutable state is the root of all evil, this is the link for you. So what we do is we then use a stream operation called range closed. This will generate a range of values from 1 to n in order. And then what we're going to do is we're going to process that range in parallel. This is another way of getting a parallel stream. You just say dot parallel. That converts the sequential stream to a parallel stream. And then for each element in this range, we're going to multiply the number 1, 2, 3 up to n by calling t : mult. So that'll call the mult method on the t variable. And we're going to multiply the running total with the latest value. And this is where chaos and insanity will ensue, because all these different threads that we show here will be calling mult at the same time, or close to the same time, and they will say mtotal times equal n, but there's no protection. And because of the way that caching works in modern multi-core processors, and because of the way the Java memory model is defined, these operations on mtotal will be working on locally cached versions of mtotal that will not be flushed and synchronized with the one true value. So you'll end up with crazy results, and you can actually run the program and see what kind of crazy results that you get. Yeah? Oh, great question. So the question is, why did I do this somewhat less common way of doing this? Because range closed is the factory method here. It's the thing that generates the sequence. So there was nothing for us to do parallel stream on at that point. Parallel stream is a factory method operation that expects something like a collection. So we need to get the data somehow. And range closed is a perfectly good way to generate data from 1 to n, but it's going to do it sequentially. So we then have to say, oh, by the way, I want you to run that in parallel, please. And then it'll arrange to do that in parallel. That's a good question. So what's happening here is all these different threads are stomping on m total, and it will be corrupted, and you'll get crazy results. There's also some other super duper subtle issues here having to do with memory visibility, which I'm not going to go into a lot of detail on at this point, but just be aware that writing code like this is going to get you in big trouble. So don't do that. So you're much better off using features from parallel streams to do this. The other thing to keep in mind here is just like only you can prevent forest fires, says Smokey the Bear, only you can prevent concurrency. So the compiler will not save you from yourself. If you want to write code like this, it'll compile just fine. The Java virtual machine will not save you from yourself. It'll run this code, however buggy and corrupting it may be. You have to know what to do. Now, the good news is it's really easy to do. Just use parallel streams, and I'll show you a parallel streams version of this code later. It's super duper easy to do, and it makes all the problems disappear. It's actually much, much more concise to do this in parallel with parallel streams than it is to write this sort of hokey implementation here with a shared object and so on. So that's the end of our discussion comparing Java sequential streams with parallel streams. Rest assured, we will go through this in much more detail later. So don't worry if it went by a little too fast. I will cover parallel streams in tremendous depth, and we will also talk about how it works under the hood, because it's really cool.